Calculus. All right, 5.3, the fundamental theorem of calculus. Now, we see the fundamental theorem of calculus is approximately named because it establishes, so look at this, it establishes a connection between two branches of calculus. We're looking at differential calculus and integral calculus. So it gives us a relationship between the two, differentiation and integration. So actually it gives us a precise inverse relationship between derivative and the integral. All right. Okay, so for the first part of fundamental term, we say discrete functions defined by this equation that you see here. So you're going to have g of x is equal to, now you need to watch out how these functions are defined so that you don't get confused. You see it's from a to some x and then f of t dt. All right, so notice it, your variable of interest here, you can see is x. However, this function here is given as f of t dt. So please don't get confused. Now I'm going to explain why, what does this mean? What is a all the way to x, or what does x actually stands for? So we say f is a continuous function on some interval a, b. Now the x that you see there, so let's see if I can change this color quickly. So this x you see here at the upper bound, they say varies between a and b. All right. So for example, if a and b is, let's say, from 0 to 2, and then I can choose my x to be any number between 0 and 2. All right. We're going to see examples. And then here they say, observe that g depends only on x. So g depends on x and not t, actually. So g depends on x. All right. And the x appears as the upper limit of the integral. All right. Now, if you notice it, they say if x is a fixed number, so when I say fixed number, it means if I let x to be some number, let's say 2, 3, 4, any constant number, notice it, this whole thing here simply becomes some, it also gives you some definite number, all right? Because you can then say that the antiderivative evaluated at the upper bound minus the lower bound. However, if we let x to vary, all right, so if you let x to vary, then this whole thing here will also vary. It will not give you some definite answer, all right? It will also vary. So indirectly, you're going to get some function as your output, all right? And it will be some function of x denoted as g of x. All right, so graphically, let's see what we're talking about. So think about it. So you have your area equals to g of x, and then you have from a to b. You see what x does. X varies, means that you can choose x to be any number there between a and b. All right, and once you choose that, therefore your g of x simply becomes the area of the enclosed region or the shaded piece. There we go. So if I choose to shift x up to this point here, then obviously my g of x is going to cover this region as well. All right. Let's do example 1. So example 1, they say if f is a function whose graph is shown in figure 2, and then they give us what g of x is. So g of x is equal to integral from 0 to x f of t dt. They say find the values of, let's start with g of 0. G of 0 means that I'm going to be integrating. So if you look at this piece here, it means I'll be integrating from 0 to 0. You can see x is 0. And we saw already one of the properties of the definite integral is that when you integrate from the same lower bound to the same upper bound, you just get 0, right? So g of 0 is just going to be 0 because integrating from 0 to 0 just gives you 0, all right? Let's try g of 1. G of 1 now means I'm integrating from where? From 0 all the way to 1. And if you notice, 0 to 1 represent this triangle here. All right. And therefore, g of x is going to be what? The area of a triangle. And what is the area of a triangle? It's just half base times height. So half times 1 times the height, which is 2. There we go. Easy. And then g of 2, notice it is going to be g of 1 which is, so g of 2, now you're somewhere there. Let me just change the color so that you guys can see the pattern. G of 2 now is a whole of this piece here all the way to 2. All right, we're looking at this whole piece here. Now, you can see that it is equal to g of 1, which we've already solved, the area of this triangle there. We did that already. G1 plus the area of this rectangle here. There you go. All right. And then if we go to g of 3, then we need to add this other piece here. Obviously, we can approximate that. G of 4, we're going to add g of 3 plus this little piece here. And then g of 5 is going to be g of 4 plus this last piece here. So that is the whole idea. Here it is just showing us that this is equal to 0. We know why g of 0 is 0, because if you integrate from 0 to 0, you just have 0. G of 1, I've already told you guys, you're just looking for the area of a triangle. You just have base times height. All right. And for g of 2, you need to add g of 1. You see g of 2 is this little triangle plus some rectangle. So you say g of 1 plus the area of the rectangle. All right. It will just be equal to 3 if you do that. And then g of 3 is going to be g of 2 plus this little piece here, this remaining piece here. And that we can approximate, approximately equals to 1.3. All right. So if you add that to 3, you have 4.3. Now notice it, for g of 4, you need to add g of 3, which is this whole piece here. We've already found that, plus this little piece here at the bottom. However, notice that because this is at the bottom of your axis of interest, T, it's going to give you some negative area. All right, you can see there we approximate it to minus 1.3. Similarly, if you find g of 5, you're going to say g of 4, which is 3, plus, again, you need to add the area of this remaining piece here, which is also negative. You see, we approximate it to minus 1.3 again, and you see in total you have 1.7. So what have we observed? That when you get to g of 5 here at the end, you end up taking this whole area there minus this whole area here. All right. Very, very important fundamental term calculus. Let's look at the definition, part 1. Let's say if f is continuous, this is very important, f is continuous on some closed interval ab, then the function g defined by g of x equal area or the integral from a to x f of t dt, where x lies in this closed interval. We say g of x is continuous on the closed interval ab and differentiable on the open interval, and we just get that g prime of x is equal to f of x. All right. Now, if you use Leibniz notation, when I say g prime, it just means d dx. Remember, g prime means derivative with respect to x. All right. So g prime of x just means d dx of that integral from a to x f of t dt, and we say that the derivative is just equals to f, this function evaluated at that upper bound the x. All right. And we say when f is continuous. If you notice it, it doesn't matter what the value of a is. Always keep that in mind. It doesn't matter what the value of a is, as long as that function is continuous on some closed interval ab. All right, including the point a itself. All right. So basically, it's just what I said before. So it says that the derivative of a definite integral with respect to its upper limit is the integrand evaluated as the upper limit. You see, derivative of an integral with respect to its upper limit, you see dx here at the bottom means with respect to x, which is our upper limit, is equivalent to the integrand. Remember, integrand is that function that we try to integrate, all right? Integrand evaluated at the upper limit. So from f of t, we just need to say f of x. So evaluate f at x, all right? Let's do some examples. So find the derivative of the function g of x is equal to the integral from 0 to x square root 1 plus t squared dt. All right. Now, if you notice it, this is already in the form. So directly, we can see that this root function is continuous. So if you apply part 1 on the fundamental of calculus, you get that the derivative g prime of x is just f of x. So it means everywhere you see t here, in the place of t squared, I'm going to replace it with x squared. So I just have square root 1 plus x squared. It's already in the form. All right. And if you notice it, your lower limit of integration, so we're looking at this number here, it doesn't affect the value of g prime of x. Very important. It doesn't affect the value. Let's look at another example. So I'm sure everyone can do this one. They say they give you f of x is equals to this whole thing here, and then they ask you to find f prime. All right, f prime is going to be d dx of this whole integral. We can just directly apply it because it is in the form. A in this case is 1, so f prime of x is just going to be, everyone knows the answer, it's just going to be x squared minus 2x plus 3. As easy as that. All right. So it's just going to be the function evaluated at x, so f of x. Straightforward and easy. All right, now it gets a little exciting. I'm going to explain why this one is slightly different. Now, if you notice it, we were interested in integrals of this form, so a to x. Now, if you notice these two examples, there's a little bit of a difference. You no longer have x, now you have 2x. All right, guys, keep this in mind. Once it changes from x to something else, maybe x squared or some constant times x, you must use chain rule. So the first thing that comes to mind, if you see anything different from this, you think of chain rule automatically. All right, chain rule. In this case, we're also going to apply chain rule. All right, but we have to start by splitting the bound because fundamentals of calculus, we must always integrate from some constant a to x. All right, so we have to start by splitting this bound into 2. So let's jump straight to the memo so that I take you step by step on how you're going to approach this question. All right, I hope everyone can see the memo. If you can't, just zoom in from the device you have. So the first one, we've already seen this one. F prime there was just d dx of, so you can see it's already in the form. So a there's 1 to x, they have some polynomial. And you know your polynomial function are very important. We say your function needs to be continuous on that closed interval a, but you know it's a polynomial, so it's continuous on the set of real numbers, so it's continuous everywhere basically. Therefore, we can just go ahead and say it's just that function when I change t to x. So this is that. And always mention that by fundamental of calculus part 1. All right, don't write my abbreviation, just write the full statement by the fundamental of calculus part 1. All right. Now for the second one, look at what happened here. I told you that this is not in the standard form that you know, from a to x, all right? This is from a to 2x, all right, where a is 0. So first thing you need to do is to try and get you have to deal with this 2x there. How do we do that? You like u to be 2x. Therefore, du dx is just equals to 2, all right? dy dx, remember you're looking for y prime, you're looking for the derivative of that integral. So dy dx becomes d dx of 0 to 2x sine t dt. And remember d dx, let me write it here. According to chain rule, if you're looking for d dx, chain rule says that you can say d du times du dx. All right, everyone should be happy with this. This is just chain rule. So please always keep in mind chain rule when you start seeing some function that differs from x itself. And how do we do that? We have d du your integral now become from 0 to, remember you let u to be 2x. So where you see 2x there, this 2x there, you place it with u, and then sine t dt, multiply that with du dx to show that you are applying chain rule. All right. And notice it, this works because you now you differentiating with respect to u. It means that this upper bound has to also be in terms of u. Always keep that in mind. You can't say d du and then here you are still writing x or 2x. All right. D du means with respect to the variable at the upper bound. All right. Now this is already in the standard form, so d du integral from 0 to u sine t dt. We can apply fundamental to calculus there. It's just going to be sine of u. All right. Remember, you always take the function or your integrand evaluated at that upper bound there. So it's just going to be, instead of sine of t, you just say sine of u times, what is du dx? We found it here is equals to 2. So you have 2 sine u, but u is equal to 2x, therefore you have 2 sine 2x. Very important by the fundamental theorem of calculus part 1. Right. So once you see a question like that, and then you fail to do chain rule, then know that you're going to lose all the marks. As easy as that. And also, guys, if I ask you to differentiate an integral, please use fundamental to calculus part 1. So it should be easy for you to spot in my exam. All right. If you see the derivative of an integral, you know I'm testing you fundamental to calculus part 1. You can go and start trying to integrate and then differentiate the result at the end. That is 0. You get the 0 automatically. I've seen that many times in my years of lecturing. Students tend to do some funny stuff. All right. So the derivative of an integral automatically, you know, we're testing fundamental to calculus part 1. Now, 3 is the trickiest of all of them. This is the hardest you can get. So once you understand this example, you should be comfortable. All right. The trick now is, instead of integral, remember that the standard form says we need to integrate from a to x, right? This is what the standard form says. But if you notice it here, let me change the color. You see we're integrating from 2x to 3x. All right. Now the trick is you need to split this integral into 2. All right. Remember I showed you that little rule that if you're integrating from a to b, but there's an adjacent interval in between, you can split the area into 2. All right. So it's more or less the same idea. So we can split, we can say the integral from 2x to 0 plus the integral from 0 all the way to 3x. Now, some of you are probably going to ask me, why do I choose 0? The first thing, before we apply fundamental calculus part 1, it says that the function needs to be continuous on some closed interval AB, right? Now, if you think about it, the sine function is continuous. It's a periodic function. Basically, it's continuous everywhere. It means I can choose this point of splitting to be any value. I can choose pi over 2. I can choose pi over 4. Any number that's going to work. All right. Because it's a sine function. Now, you need to be careful. For example, let's say that I change the sine function to, let's say, 1 over x. Automatically 0 doesn't work anymore. You know why? Because 1 over x is not defined when x is 0. You see, so you always need to think about it. So you can choose any number to split this interval into 2, or your integral into 2. Your choice of splitting there, you see here I'm choosing 0 because I know sine is continuous everywhere. So to make my life easier, I'll just choose 0. But be careful, always look at the function and see if your choice, your choice of A works. All right. Now, if you notice it, I introduced a negative sign. I'm sure some of you are asking, where's the negative now coming from? We saw that already. This is a standard form. Therefore, if I give you something that looks the other way around, so if I give you integral from x to a, obviously, you know, for you to get to this, you need to swap the bounds and introduce a negative sign. And that's why we have this negative sign here. All right. Because we had integral from 2x to 0. But we want the integral to be from a constant a to our function. All right. Now notice it again. This is not in standard form. I'm going to highlight that. Why? Because we want the integral from a to x, but here we have 2x and 3x. So what comes to mind? Chain rule. Very important, chain rule. Once you see it's different from x, you think about chain rule. For chain rule, you can make some substitutions. So let u to be 2x, du dx is just 2. Let another variable v to be 3x, dv dx is equal to 3. Now, notice it, dy dx is just going to be, we need to differentiate this piece here. So it's going to be minus, so we'll just take the minus sign in first. So minus d dx of the integral from 0 to 2x sine t dt plus, so we split out the derivative. So d dx from 0 to 3x sine t dt. Now look at what chain rule says. Chain rule says d dx can be written as what? d du times du dx. So you can see I have d du. Immediately I see d du. That statement that means my upper bound there has to be in terms of u. And it's true because we let u to be 2x. So where you see 2x, just put u there for your upper bound. And make sure you multiply by du dx so that it's complete. Your chain rule is complete. Go to this other side. D dv, it also tells me that my upper bound there has to be in terms of v. And it's true because we did let v to be 3x. So it means that where I see 3x on the upper bound, I can replace it with v. And again, just multiply by dv dx so that the chain rule is complete. Then from there, let me just highlight. Fundamental truth of calculus, part 1 can be applied. So here, the rule is satisfied. Here as well, we can apply fundamental truth of calculus, part 1. All right. So this first one here will just become minus sine of u. This second one will just become sine of v. It's as easy as that. And then you just need to multiply by this dv dx and du dx. Easy as that. All right. Let me zoom in so that you see what that final answer looks like. All right, so you can see at the top, we have minus sine u times du dx, which was 2, sine v times dv dx, which is 3, but always substitute your value for u and v. So you have minus 2 sine 2x plus 3 sine 3x. And very important, by the fundamental theory of calculus part 1. All right. Now, the next example, I'm just going to open it quickly. It also requires us to apply fundamental theory of calculus part 1. Let's see if we can move to the slide quickly. There we go. So with example 4, I'm not going to explain because everyone knows what to do. But let's see if you guys really understand. Now, if you look at this, d dx integral from 1x to the 4 sec t dt, notice it. This is strange guy there, x to the power 4. That guy is very strange because it doesn't look like the standard format. What is the first thing you think of? Chain rule. Yes, the person who thought of chain rule is correct. So you're going to let u to be x to the power 4 and then find du dx and then apply chain rule. So this one is straightforward. Now, what you do for the second one is similar to what we did already. You need to split this integral into 2. So you need to split from x to some upper bound plus integral from some number all the way to x squared. Now, your choice of splitting, remember what I said, you need to consider this function there. E to the power t squared is continuous on the set of real numbers. It's continuous everywhere. So to make my life easy, I'll just put 0. It works. All right. But always check. Don't just be quick to use 0 because sometimes 0 may not work. I told you, for example, if the function was 1 over x, so if I give you 1 over x or ln of x. So if I give you ln of x, you know that you can split at 0. If I give you 1 over x also, you can split at 0. So you guys should be able to do example 4. The solution is available on Blackboard. All right, now let's go to fundamental theorem of calculus part 2. What does it say? What does fundamental theory of calculus part 2 say? It says that if f, again, Guys, this is so important. If f is continuous on a closed interval, so your function always has to be continuous in that closed interval AB, all right? Then we say that the integral from a to b, f of x dx, is f of at b minus f at a. Remember, we call this f the antiderivative, all right? So for you to find the integral of a function, you just need to find the antiderivative of that function, and then you apply the evaluated at the upper bound minus antiderivative evaluated at the lower bound. All right, and f is called the antiderivative of f because if I differentiate capital F, I just get my original function f. All right. All right, this one's you guys should be comfortable doing this one. So if they say the integral from 1 to 3 of e to the power x, this should be very easy. You just need to find the antiderivative for e to the power x. Remember, the antiderivative of e to the power x is just e to the power x, right? Why? Because if you differentiate e to the power x, you just get e to the power x. So you just need to now evaluate that antiderivative from 1 to 3, and that simply becomes e to the power 3 minus e to the power 1. Easy as that, right? For 2, find the area. Remember, when they say find the area, they're talking about integral. Remember, integral means area under a curve, right? So find the area under the parabola y equals to x squared from 0 to 1. Indirectly, they tell you that find the integral from 0 to 1 of x squared. All right, definitely I'm not going to do this. Everyone can do this. Straightforward and easy. You just find the antiderivative of x squared, which is x cubed over 3, and then evaluate it at upper bound minus lower bound. All right. Now for 3, we need to integrate from 3 to 6 of dx over x. What is the antiderivative of 1 over x? It's ln. It's the ln function. All right. Specifically, ln absolute value of x. All right. And all you need to do is evaluate it from 3 to 6. All right. So you get ln of 6 minus ln of 3. All right. And then find the a under the cosine curve from 0 to b, where they say b lies between 0 and pi over 2. Again, it's just integral from 0 to pi over 2 of your cosine function. Very easy. All right. And you know that the antiderivative of cos is just sine. All right. The antiderivative of cos is sine. Why? Because if you differentiate sine, you just get cos. So it will just be sine of x evaluated from 0 to pi over 2. So you see, it's very straightforward and easy. Guys, go practice. Now, guys, this is a mistake that I don't want you guys to make in my test. Because no matter how many years we've been studying this, people still make the same mistake. Now they ask you, what is wrong with this calculation? Let's go through it together and see. We have the integral from minus 1 to 3, 1 over x squared dx. Obviously, 1 over x squared, you can see is x to the power minus 2. If you find the antiderivative using the power rule, it becomes x to the power n plus 1. Remember what the antiderivative of x to the power n is. The antiderivative is just x to the power n plus 1. So if you integrate that, you have n plus 1 divided by n plus 1. All right, so that's just what the formula tells us. So if I apply this formula there, I'll have minus 2 plus 1 is minus 1 divided by minus 1. So it's minus x evaluated from minus 1 to 3. X to the power minus 1 just means reciprocal. And then if I do that, okay, guys, quickly in the comment area, can someone tell me what is wrong with this calculation? Quickly. All right, if you feel that everything is okay, can you also tell me that it's okay? Is this calculation okay? That is what I'm trying to check. I mean, we've gone through it together. We see it's heading towards minus 4 over 3, but what is wrong with this calculation? Can someone tell me quickly? Look at it carefully and tell me what is wrong. Anyone brave enough to say something? All right, it looks like you guys haven't spotted this. Okay, if you haven't spotted what is wrong, then it's not the end of the world, but these are stuff that you should be able to spot in my test. I will show you quickly. Remember, when I explain fundamental two of calculus part 1 and part 2, what is the first thing that I stressed about? I said the function f needs to be continuous on a closed interval ab. Now look at this function. The function is 1 over x squared. Is it continuous from minus 1 to 3? The answer is no. Remember, there's 0 in between minus 1 and 3. The function itself is not continuous on that closed interval minus 1, 3 because it is not defined when x is 0. You know 0 lies between minus 1 and 3, right? So that it means that everything we've done here is invalid, is 0. If you do this in a test, you get 0, right? It's completely unacceptable, right? I'll teach you guys how to solve this later on. We're going to do that when we get to 1b. We call this kind of integral improper integrals. All right, they call improper integral. It means you have some sort of discontinuity along the bound. All right, so your function 1 over x squared is not continuous on this closed interval. Therefore, you cannot apply fundamental of calculus part 2. All right. Some of you still doubt why is it not continuous. I told you 1 over x squared is not defined when x is 0. You can see that within this interval minus 1 to 3, 0 lies somewhere there. All right. 0 is part of that interval, and the function is not defined as 0. It means it is not continuous across the whole interval. Therefore, we cannot apply fundamental of calculus part 2. I hope that is very clear. All right. Now, there are more examples for you. So, as usual, just get the antiderivative, apply fundamental of calculus part 2. That says you evaluate this function, the upper bound minus the lower bound. The same thing happens here. Remember, if you integrate 3 over x, you just have 3 times ln absolute value of x. And then here, apply your exponential rules. So x times x to the power half is just x to the power 3 over 2. And then the antiderivative of sec times tan is just sec. All right, because the derivative of sec is sec times tan. Therefore, if you integrate sec times tan, you just get sec. All right, so it'll be sec of power 4 minus sec of 0. And then 4 and 5, we back to, you see, immediately I say find f prime. You know we're talking of fundamental calculus part 2. Guys, when you do fundamental calculus part 2, don't tell me that by fundamental calculus part 2. Only tell me that when you do this, guys, here. When you differentiate an integral, you need to tell me fundamental calculus part 1. All right. So I know some of you will become so used to saying that by fundamental, even when you do part 2, you want to tell me part 2. But it's fine if you have enough time to write all of that. I'll just smile and still give you your mark. But where I'll check that you've mentioned is this one. This is where I'm going to pay more attention. If you do a part 1, you must tell me that it's fundamental to calculus part 1. But I don't care if it's actually part 2. If you tell me on or not, I will see through your applications. All right. So the first one here, obviously, is in the form. It's a polynomial. It's continuous on the set of real number. Therefore, if I choose 0 to x, it's fine. X can be any value after 0. So in this case, we can just say f prime of x is x squared minus 3x plus 2. Look at the second one. It looks like it's in the form, but the only problem is that instead of integrating from a to x, we have from x to some number a, which is 2. So you just need to include a negative sign and then swap the bounds. So bring 2 now to the bottom and take x to be the upper bound. All right. And once you do that, it will be in the form. And then you can just say minus sec of x. All right. It's as easy as that. We still have a little bit of time. Let me just go to the memo so that we see what are the answers that you get if you do that. All right, so let's go to this example. So the memo is available on Blackboard for those examples. I wrote them out so that you guys can practice. You see the first one that we did is just e to the x. If you integrate, it stays e to the x. Evaluate it from 1 to 3, just e to the 3 minus. If you integrate x squared, you just have x cubed over 3, and then put 0 to 1, simplify 1 over 3. For 1 over x, lean absolute value, right? If you fail to put absolute value, it will cost you at some point, so you're going to lose some marks, all right? So integral 1 over x is lean absolute value. And remember, absolute value of a positive number, it just stays the same. So it should just be ln of 6. If you choose to still say ln absolute value of 6 minus ln absolute value of 3 is equal to ln absolute value of 2. If you do this, I will still give you the mark, but it tells me that you really don't know what absolute value is. Because if it's positive, you're welcome to take away the absolute value sign. So absolute value of 6 is just 6, right? Yeah, if you integrate cos, we see there you just get sine, and if you evaluate it from 0 to pi over 2, it's easy. Sine of pi over 2 is 1 minus sine of 0 is 0, so it just gives you 1. And then for 10 and 11, the same idea. You just integrate 2x minus 3, you get x squared minus 3x. Apply a fundamental calculus by 2, so antiderivative at the upper bound minus antiderivative at the lower bound. All right, similar to this, you see here, if I integrate here, I have x to the power 3 over 2 plus 1, which is now 5 over 2. I need to divide that by 5 over 2. So if you divide by 5 over 2, it's the same as multiplying by 2 over 5. All right. And the integral of 3 over x is just 3 ln absolute value of x. And they apply fundamental to calculus by 2. Again, you're good to go. And then for 12, we said that the integral of sec times tan is just sec. Because if I differentiate sec, I get sec times tan. So you just need to take sec of pi over 4 minus 0, and this is just root 2 minus 1. Right. And then this one, once you see d dx, you know we're talking of fundamental of calculus part 1. So d dx, integral from 0 to x, it's a polynomial, you know it's continuous everywhere, so you can just go ahead and say your answer will be equals to f of x. All right. Remember, this is f of t, it just becomes f of x because you want to evaluate the function at the upper bound. All right, so you have x squared minus 3x plus 2, and you say by the fundamentals of calculus part 1. And then for this last one, the only trick here was just to swap the bounds. You see, it's from x to 2. I'll just introduce a negative sign, and I say from 2 to x. It is now in the form, so I can apply fundamental of calculus part 1. It just becomes minus sec of the upper bound, which is minus sec of x. And then I say by fundamental of calculus part 1. All right.